All right, so yeah, today I'm going to be telling you about the biography of a mountain, the biography of these mountains here, and we're going to jump straight in with a video. You guys can hear that, hopefully. Geologists are often described as rock detectives. Like detectives, geologists are trained to make careful observations and to gather evidence. A detective will do this to tell the story of how a crime happened. A geologist will do this to tell the story of how a rock formed. And that can tell you an even bigger story about how an ocean dried up, about how an extinct animal used to live, or about how a mountain range formed. These stories are written in the rocks in their own special language, and geologists need to learn that language. So, how do you read a rock? If you think of geology like a language, the chemical elements are like letters. You put letters together to make words, like you put elements together to make minerals. You put words together to make sentences, like you put minerals together to make rocks. So understanding minerals is key to understanding the stories of rocks. But if a detective only asked one person about a crime, they probably wouldn't get the whole story. And in geology, it is unlikely that just one mineral will tell you everything you need to know. Different minerals will tell you different parts of the story, depending on what they experienced. In order to link these stories together, you need to work out what these minerals have in common. This is where you look at the elements that make up the minerals. That's what my PhD has been all about. I've spent the last 4 years shooting electrons and lasers at different minerals to find out their chemistry. I've investigated lots of rocks and minerals, read through the letters, words and sentences found within them, and have pieced together the different parts of the story so that I can now share with the world the biography of a mountain. All right, so there we go, the biography of a mountain. And the mountains that I'm going to be talking about are the Himalaya, this magnificent 3,000-kilometre stretch of mountains that formed when the Indian subcontinent moved northwards and collided with Eurasia about 50 million years ago. The most interesting part of continental collision for me is what happens in the heart of a mountain range. I'm interested in the rocks stuck down at the bottom of the mountain range, the ones that experience high temperatures and pressures. More specifically, the rocks that get so hot that they melt. These molten rocks end up cooling down, solidifying, and turning into the rock granite. This process of melt generation and the formation of granite is a really important process when you're building a mountain belt. Granites are really important for moving different chemical elements around different rocks as they melt, move, and cool. They influence how strong a mountain is, which can change over time, and they tell us really important information about the conditions that the rocks experienced. Now, geologists think about these conditions in terms of pressure, temperature, and time space. What is happening to a rock, when, and where? So this line here shows how a rock in the core of a mountain belt changes over time. When collision starts, the rocks go through a period of burial and they go through a period of burial where temperatures and pressures increase as it gets very deep under loads of other rocks. They then experience exhumation, where the rocks cool down, decompress, and make their way back towards the surface. And granite can form in a number of different places along this path. The vast majority of granite that's found in the Himalayas forms along this part of the path during exhumation at around 22 and 15 million years ago. And the way that we know where it forms on this path is due to the minerals that they contain. So the aluminosilicate minerals are common in granites in the Himalaya, and depending on the pressure temperature conditions at the time that they grow, you'll get one of these minerals. So the granites that form at 15 and 22 million years contain the mineral selimonite, which only forms in this part of the pressure temperature space. But there's also these rare granites that instead of containing selimonite, contain the mineral kyanite, because they formed at higher pressures. We know a lot about the selimonite granites because they're normally kilometre-sized bodies of granite, but we don't know much about the kyanite granites. They're not as common, they're much smaller, and so their story is much more of a mystery. So, like a detective, I decided to investigate them. And this is what kyanite granites look like. This is a photo taken in the country of Bhutan in the Eastern Himalaya, where I went to go and collect some samples. These are rocks called MIGMATITES, and that means mixed rock because they're a mixture of this dark rock and this white rock. This dark rock is an unmelted rock called schist that formed due to the metamorphism of seafloor sediments, while the white rock is our granite, and the granite represents parts of the dark rock that have melted and cooled and crystallized in place. Now, Lego Me said in the video that understanding minerals is the key to understanding rocks, and that I have been doing that by looking at the chemistry of minerals. And there's three main minerals or characters that I interrogated. We've got kyanite, muscovite, and zircon. All of them are found in the migmatites, in both the unmelted schist and the formerly molten granite, and each character plays a role in our story. Kyanite is this wonderful bright blue mineral in the photo here, and that's the mineral that indicates the pressure at which the rocks formed. Muscovite is this yellow mineral in this thin section photo here, and that's the mineral that's responsible for breaking down and forming the melt. Zircon is this tree ring zoned mineral seen in this cathodoluminescence image, and that's the mineral that records time. So let's see what these minerals had to say. As I mentioned before, kyanite is a key marker that the rock it formed in formed at high pressures. But what if there's a kyanite in a rock that didn't form there, instead it just ended up there, like it could do if there was a melt that was moving around these rocks? And then we make mountain-wide interpretations based on the assumption that that kyanite formed in that rock. That means that we really need to understand how the minerals grew if we're going to accurately use the pressure temperature information they give us. So in order to understand how these grains grew, I looked at their internal textures by taking cathodoluminescence images of hundreds of kyanite grains, which is what you can see here. By doing this, I was able to identify different types of kyanite and then individual zones within those grains that represent different ways that kyanite grew. For example, the interior of a number of these kyanite grains, these complex Z1 and Z4 zones that you see here, represent metamorphic growth of kyanite before we had any melting. Some of these kyanite then found their way into a melt where they were able to continue growing, forming these distinct, differently coloured Z2 and Z5 rims around the outside of those existing grains. Then there were some grains that grew directly from the melt. They don't contain the complex cores, they don't show much zonation. These are newly crystallized kyanite grains with Z3 zonation. Now, cathodoluminescence images reflect the underlying chemistry of the kyanite grains. And when we look at the chemistry of these different zones, we can see that the different types of growth have pretty distinctive compositions. In this plot, the absolute concentrations have been normalized to averages found in that particular sample for reasons I don't have a chance to get into right now. But this plot shows the relative enrichment or depletion of different elements for each of the growth zones. And we can see that the Z1 and the Z4 zones are relatively similar to each other as they both form during metamorphic growth. The Z2 and the Z5 rims that grew around the outside of these cores are also similar to each other, both showing really strong depletions in magnesium and enrichments in chromium. Then we look at the Z3 growth, which is the growth of the new kyanite in the melt. Now, if Z3 growth happened in the melt, we might expect it to have a similar composition to the Z2 and Z5 zones, but we don't. They've got higher scandium and titanium, they're depleted in chromium, and they've got this distinctive enrichment in germanium. So why are these grains so different? Well, to answer that question, we're going to turn to another of our characters in our story, and that is muscovite. Muscovite's found throughout the migmatites, and as I said before, it's the mineral that is responsible for the formation of melt through something known as the muscovite dehydration reaction. Once melt is formed, it's possible that new muscovite will crystallize in that melt as it cools down. And similar to kyanite, I was able to identify a number of different types of muscovite grains. The one that I'm going to draw your attention to here is muscovite C. This type of muscovite is found around the outside of kyanite grains that have this particular jagged, corroded shape, like the ones you can see in these images here. And we interpret this muscovite to have formed due to a reaction between the kyanite and the molten rock during cooling. And we can look at the chemistry of the different types of muscovite in a similar way to how we looked at the kyanite. There are more trace elements found in muscovite than there are in kyanite, but this diagram works in the same way as the previous one. There's a lot more variation between the different types, but I want you to focus on muscovite C grains again, the grains that are growing around that corroded kyanite. And you'll notice, amongst other things, that they've got this distinctive enrichment in germanium as well, just like our Z3 kyanite growth. So it looks like these two types of kyanite and muscovite have something in common. So what do we think happened here? Well, here's a schematic diagram that first shows that we have initial growth of metamorphic kyanite before we have any melt. These kyanite grains then got incorporated in the melt. There was continued growth around the outside of them, forming Z2 and Z5 growth rims, but then some of those kyanite grains started dissolving in the melt, giving them that corroded shape. When this happened, we think that germanium was released from the kyanite into the melt. Then, when the melt reacted with the kyanite to form that muscovite C, that muscovite incorporated some of that germanium, as did the new kyanite grains with the Z3 growth. That's why they're both enriched in germanium. So there was this geochemical exchange going on that we weren't expecting to see, and it demonstrates that different minerals can have geochemical conversations where they can swap elements, which is really cool. And this is all consistent with kyanite growing when there was melt around, which means that most of the kyanite found in the granite did in fact form in the granite. Once we've demonstrated that, we can accurately pin where in pressure temperature space these migmatites formed. And that means that we can then start to understand when these rocks formed. And to do that, we look at the mineral zircon. Zircon is a beloved mineral by geologists because it has lots of uranium in it that can radioactively decay into lead, meaning that if we measure the amounts of uranium and lead, we can calculate how old the grains are. And from this one tiny grain with these tiny laser spots, we found evidence that the zircon grew continuously in the melt for around 6 million years. That's a remarkable record that just this one grain has recorded. It's kind of cool. If we then combine all the zircon data together from different grains, from different samples, and we look at the actual ages that we get, we can see that there's 2 time periods where we get lots of zircon growth. That's what these zircon peaks show us. And they're thought to represent the main periods of melt formation, which are around 20 and 15 million years ago. Now, this is around the same time that we see the selimonite granites forming elsewhere in the Himalayas, which is not what we expected. We thought these kyanite granites would be older, around 30 million years old, because that's kind of how the PT path goes. And other Himalayan researchers have also predicted this, and they almost assume that kyanite migmatites must have formed 30 million years ago. But my work suggests that that isn't the case. Does that mean that we've somehow caught the wrong guy? Well, no. Instead, it means that the conditions that form kyanite migmatites in Bhutan may have persisted for longer than we thought, and that different granites can form at different times, under different conditions, in different parts of our mountain belt. Simple, right? And so to conclude, understanding in detail how a mineral forms is crucial for any subsequent interpretations made. Different types of kyanite growth can be identified through cathodoluminescence imaging and trace element analysis. Minerals like kyanite and muscovite are able to exchange trace elements via the melt, and kyanite migmatites in Bhutan formed much later than expected, challenging a number of assumptions in Himalayan tectonics. And that is the biography of a mountain. Thank you very much.